This is part 14. This was actually filmed just a minute after part 13, and we're just about to finish our epic introduction to A-star algorithm for pathing our character. It's taken like 4 streams, but you know, in the grand scheme of things, like 8 hours to do, you know, to get pathing working and working correctly in our game is not much time. So I think we're working at a good pace. So in the last one we got distance-based pathing working. I wish I had a nice example. Here we go. See, so it's quicker to go around than it was to walk through. I wonder, yeah, that one's quicker. Nope, that's quicker to go around. 1, 2, 3, 4. Huh. Interesting. I'm just trying to count it because I'm kind of curious, like, how much time it takes. But anyway, yeah, you can see with some of it. Oh, that's interesting. There was like a really cool example right here where it walked. Yeah, see where it went through the water here and then across here, because it took more than 3 to go around just the edge of that. Anyway, so it's cool. It takes more to walk through water and the lava, which is orange, than it does to just move around. So that's awesome. Got that. Now we are going to make our pathing smarter. There's 2 ways to do that. One is to do this greedy best first search, and then combine that with our Dijkstra's algorithm, which is what we're already using to calculate priority and go through the quickest path. And if you combine those 2, you get A-star, which is kind of like the you know, ultimate one. It's kind of like the gold standard for you know, pathing algorithms. You'll see it used all over the place. Anyway, so this, again, redblobgames.com has this great tutorial that explains it all, and this, you know, it's built with these really cool visual elements like this, where it shows you what exactly is happening so that you can understand. So this shows you what the Dijkstra's algorithm does. This does greedy best first, and then this is A-star. And so greedy best first doesn't always get the shortest path, which is why, like, you'll notice it often looks at far fewer places than A-star in Dijkstra's, but it doesn't necessarily get the shortest path. A-star guarantees the shortest path while also minimizing the number of spaces. So unfortunately, like, to get to here, it has to look at a lot more spaces, but at least it confirms that yes, this is the shortest path. Dijkstra's algorithm needed to look at nearly the entire board to understand that. So cool. So let's go and make it happen. So we're on greedy best first, and so all we need is this simple heuristic to see, like, hey, is this grid closer than, like, is this new location closer than the old location? See, so this expands out in any direction. This one expands out and goes like, yeah, these are getting closer. If I go here, I'm getting kind of further away from my goal. That heuristic could change dependent on, like, if you don't have a strict grid like this, you might have a heuristic that is more complex to determine whether or not you're going in the right direction. But in this case, we're using a grid, and so that makes it a fairly simple heuristic. So we're going to go into our forest map. Not our forest map. We're in, well, no, this is our forest map that we want to use. Yeah, not the builder map. Okay, so we're going to add this here. So why am I putting the heuristic here? I'm putting the heuristic here because it's associated with the map. If we were using a different kind of map, like I said, we might have a different heuristic. So this one is actually a pretty simple one. And actually what I'm thinking is, we'd have to do conversions. Oh yeah, these for us, these are going to be I's and J's. Because our X and Y are actual like visible coordinates on the screen, whereas IJ are the grid coordinates. Yeah, so I think this is actually just going to be fine. It just needs to be, what is it? I think Lewis, that math, something like that. And now, if you recall, this is pretty different than our A-star, or our previous, which was our Dijkstra's algorithm version. The Dijkstra's algorithm had this whole cost notion, etc., etc. This cuts out all that cost notion and just does a heuristic. So let's go recreate that. We save this greedy best first search to show what this looks like. So we're gonna put this over here so we can see it while we work. That was Dijkstra's. Here is heuristic, and here's, okay, so there we go. I am going to get rid of everything on this side. I don't think we need it anymore. Now that we have a priority queue that works, we can get rid of our temporary code. What was this? That was saving our old code, but that's fine. We've actually saved it into different files. Cool. I'm going to switch back to a single layout. And okay, here we go. Okay, so we've got our priority queue. We're going to go through current. I want to get rid of this. We don't need that anymore. Yeah, we actually have our breakout here where they have it here. That's totally fine. That shouldn't cause a problem. Okay, so if, oh, you know what? I wonder if moving this to here actually gives you the chance. I'm just thinking that there might be certain cases where there might be a neighbor that's quicker to get to the location, but that's really unlikely, I think. So we're not going to worry about that. This might actually come into play when you have something where the cost of going, let's say the player was right here, and say the cost of coming through this way is like different than the cost of coming through around like this. That could break that, but we don't have any cases like that, so I'm not really going to worry about that right now. So our break is in a little slightly different place. But anyway, we're going to go through our neighbors. Now this goes back to our more simplistic version, which is similar to our old code, which was, I should have put these searches, given them a name so that they're sorted together. Anyway, it's this: if not in self came from neighbor, or not self came from neighbor. Yeah, this just checks if it's not in self came from. We have a better version of this, so we're just gonna do this as a reminder. We don't have cost so far in this at all, so we don't even need cost so far. So in this greedy best first, let's get rid of cost so far. We can get rid of that. We don't need to calculate costs. Oh no, what did I just do? Actually don't think I need to save that. We were just gonna do this. It's gonna be as simple as this. If it's not, get location. Oh, this needs to be self. Get location from table. Self dot came from. Next neighbor. Okay, so if next neighbor is not in came from, then what we need to do is do priority. Get rid of this. Priority equals heuristic, which is going to be map heuristic. Goal. What is goal? Oh yeah, we have goal. And next. Great. And put next neighbor priority. And then insert it into the table, came from, next, blah, blah, blah. And then we get the actual path. And then we update our priority queue. So again, this might not find the shortest path, but it should still path. And should do it greedy in a more greedy fashion. Now, unfortunately, oh yeah, we're not even using this right now. So let's go into the map. And, oh wait, not the map. We don't need the map. We need is builder. No, don't even need the builder. Here we go. Instead of a star, we're going to do bulb greedy best first search. But we're going to leave the name so that we can still use it. So this is just to make sure that this is not broken. Bulb greed. I gotta actually make it the correct file name. There we go. Okay, play. So, oh, 146. Oh, let's look at our map. Okay, so we have our heuristic. I just realized I did something wrong. This should not be A, it should be goal. Right, yeah, goal. A is goal. B is next. That'll make that code a little clearer as well, a little more understandable. Okay, next. What did I miss? Oh, I probably used next. It's a function value. Oh, yeah. Don't. Oh, I know what I did. In our greedy best for search, neighbor. Yes, I put next. You don't want to use next. Okay. Okay, so this is working now without actually doing what he does here, where he makes it visible. We're not actually going to see that this is any better or worse. We're just going to see that, hey, it's happening pretty quickly, and it's just moving around. So we're going to leave that for now. I don't actually mind if that, like, ideally this is correct, and we could go through all the stuff to make sure it's correct, but we're not going to, because what we really care about is our A star. And so we're going to finish our A star, and then we're going to try to see if we can find a situation where the A star and the Dijkstra would take different paths. I actually don't think they're both going to find the shortest path, so they're actually going to be the same. So yeah, we may experiment later to figure out if our A star is actually doing a nice A star like this. But we may not. We'll see. Let's finish it up, and then I'll take a look at demonstrating it. So all we're doing is we're taking Dijkstra's algorithm, and then we're adding the heuristic. So what it's doing is it's saying, like, hey, we're going for a new cost, and we're going to take the cheaper of the new cost. We're also going to add the heuristic to know whether or not we're getting further away or not. Now, the interesting thing is that this does not distinguish between, like, let's say a high heuristic. So something is 10. Oh yeah, that makes perfect sense, I think. Where, like, if this heuristic, because of the way we're doing it, we're just doing a very simple, absolute value distance between the x and the y, and our cost is actually, like, just a simple value, like 1, 2, 3 or whatever. What I worried about is, like, that undue weight will be given to the heuristic, but we shouldn't have a situation where we're checking a tile that's, like, super far away from the previous tile. So this difference is not going to make huge difference. This should be a difference of, like, 1 or 2, not 10. So it's not going to sway it. So anyway, that's great. That means that all we have to do to get our A star is really simple. One, we need to change our player back to use A star. Let's just do that. Save that guy. And then from this, it's not the breadth first search, the greedy breadth first search. Why am I not seeing it? I don't know my alphabet. Okay. All we have to do is take our little heuristic, map heuristic, go into our A star, and add that to the cost. Bam, save that. There we go, and that should be our heuristic. Now we should have A star working. Oh, this is interesting. Oh, I never looked at the companion guide. So just as a note, it says, like, if you're ready to implement this, like, go use a library. Like, don't write it yourself. Why are you writing it yourself? But if you are writing it yourself, here's a companion guide. Now, the cool thing is that he's got all these different things. So breadth first search, early exit, Dijkstra's A star, all in Python. Then C++ versions, then a C# implementation. It's interesting that he didn't break up the C# in the same way. Looks like he might have, but not entirely sure. And then we have optimizations. Okay. Sorry, I'm just reading through some of this, and you should too at Red Blob Games. So yeah, optimizations for looking at fewer nodes. Yeah, using a different queue, like breadth first uses simple queue instead of priority queue. That's smart. Then search stuff. Yeah, cool. So that's interesting. That's good, like, food for thought. Also, there's this great thing on Ugly Path like, why don't my paths look straight? So there's a lot of short paths, and it just takes an arbitrary one. So you can straighten the path by using a string pulling algorithm, guide the paths in the right direction by adjusting the heuristic that are nice, or not use a grid. So those are cool. That's a really cool thing. I don't think we care right now about how pretty our path is, but depending on the game you're making, that might be something important to you. So anyway, we have completed that. That should work. Let's just verify that it plays. And our character still runs around and looks like he's taking the shortest path here and there. I like this water one because it has some really good examples of what is closest. Let's do a nice... This should actually help us a lot if we just do this. There we go. That should give us some interesting stuff to work with. I think if we do this, put the river around this side like that, we put dirt here, that could be good. All right, let's save that. Darn it. I don't know why I'm loading in it, or we don't need to do that. Okay, let's play this. This should give us some cool examples. Yeah, there you go. Yeah, this is quicker than going around on either side, right? Like just go through the lava. It's neat. But if you're here, I was hoping that it would go through the water, but I guess that is a little bit too distant. Let's see if we went through some dirt there. That might be enough. Yeah, see here it's closer. Ah, dang it. Yeah, it's still not enough for him to go around. But anyway, as you can see, it's like, yeah, it's closer to just go through the lava. But then if you're going down here, look at how far you can go, and it's actually quicker than taking a path through lava. So that's great. There we go. We got it done. Ship it. Okay, so now we have a nice A-star algorithm. So we've got enemies that these are just dumb enemies. They just go back and forth. They just ignore everything, just move wherever they go. What if we had an enemy that followed the player? Why don't we do that? Oh, that's an interesting thing. What I'm trying to think about is there's another way of doing this algorithm. Like right now, we skip out and just say you can't path to something if we can't actually get to the end location. The interesting thing is we could also have it just try to get to the nearest location that it could get, which means that in the end, so we're going to call this A-star. We're going to do a couple things. One thing we're going to do right off the bat is we're going to save this. We're going to make another one that we're going to call star closest. And this is going to get us like closest to something, even if we can't actually get to it. And now we're going to change this name because I'm going to go through and change all of these actually so that they're not called bulb A-star. They're actually named after whatever they're named. So let's go ahead and do that. Okay, so that's A-star. Oh, yeah, okay, good. Closest file. I thought I was looking at the wrong file. Yes, A-star is still named A-star. That's great. A-star closest. We're going to call this one search. Great. have the best first search. We have the breadth first search. Let's do that. And we're going to go ahead and save all these. As a reminder, after the stream, this is all going to be up on GitHub, so you can just go and grab the code and use it. That should be great. Okay, so we've saved all those. Okay, so now what I want to do is this closest. What we want to do is, if what it currently does is, if it can't get to the path, it's eventually going to return nil. And like we've seen, if we can't get to a location, say like in the middle of this tree, it's just going to say like, hey, could not path the location. There's just no way to get there. Instead, what I want to do is put me at the closest location that we could find. So what we're going to do is... So here we get actual path of the next neighbor once the next neighbor is the location. Instead, what we want to do is we want to say the cost so far. So we've got the cost so far for a bunch of elements. As we've been going through and doing the cost so far, we have been keeping track of where they came from. Yes, because we're putting the came from. So anything that we have the cost so far, we also have the came from, right? So what we want to do is we want to find a place that's the closest. Now, how are we going to find out what's closest? That is a good question. Now, my immediate thought was that we would look at the cost so far and find out which one is the cheapest, but that doesn't actually make any sense. This is an interesting problem, because it's like, how do you determine what is closest? So if something's here and we can't get to it, what is the closest place we can go? Like, we can't go to this tile. Well, it's one of these tiles. But then, interestingly, like if we had, say, oh, let me go back to building. If we had, say, trees around here, the closest tile could be any of these, depending on what is actually accessible. So what I'm trying to think is, like, how do we determine? So once we've gone through this and we've finished, we have put in every single tile and the cost of every single tile. Let's go look at this. So, like, think about it this way. Where is this? Okay, so if we start this animation, we've gone through and we have done every tile that we could find, and we haven't found the player. But we do have costs for all of them. Where is the version that shows the cost? Oh, the Dijkstra's over there. Here we go. Wait, no, that's not what I want. Here we go. Nope. This one. Oh, he doesn't have one that expands like that. But anyway, we've gone through and found the cost of getting to any location, right? So now that we've found the cost of any location, I guess what we want to do is we want to start from the goal and then keep moving out until we find a location that is near. Interesting. So I guess what we actually want to do is figure out if we can actually get to the player. If you can't get to the player, then we have to, like, move outward and find a place that we can get to. Now, the thing is, if we've figured out that we can't get to the player, then one of the things we've done is we have figured out that, like, all the places we cannot go to. So what I want to do is this. Let's put the player in a block. Yeah, so we should have figured the distance out for everything around it. I wonder if there's a nice way that we can verify that. Okay, yeah, here we go. This will be cool. This is why I like this, because you can test these things. So look, so we've gone in all these directions, and we've found, like, hey, here's the things that are closest, right? These ones, we found that we can get to them, but they're not close. So using our heuristic, we can figure out which one is the closest to the player, I think. So with our closest, what we want to do is basically, if we didn't find this, if we didn't already return here with something, so we're going to go like this. Didn't find path to location. Try to find closest path. Okay, so what we want to do is we want to go through all of our locations that we have in came from, right? Came from indicates a tile that we actually could have gotten to. So we're going to get pairs in self dot came from. I think this is just going to be this. Pairs in self dot came from. So what is in self dot came from? Well, we're going to have neighbor and current. Let's see. Well, this just tells us a tile. So what we actually care about is just tile, which is where we were going, which is going to be the first thing in the pair. Because we're putting that location into the table. That location. Okay, so in our came from, we have an I and a J. Interesting. Since we already have an I and a J, we can actually do this smarter, potentially. What I'm thinking about is that what we would do is we would start with an I and a J of the player, and then we would step out 1, so we'd subtract 1 I, add 1 J, blah blah blah, and then we would keep going with that, making a bigger and bigger radius until we hit the edge of the screen. Now that's not going to be necessarily optimal, because if you have something like this where you actually could get I'm trying to think, where you could get really close to the player. See if we have a player here. What I want is, let's say, yeah, something like this, where you can get closer to the player. No, I think that would actually work. Like, that might actually get you the closest to the player. So why don't we try that? So we want to have an expanding, ever expanding boundary around the player. And we just want to make sure that we have open tiles. So what we want to do is, let's say, we're going to start with 1. And then what we're going to say is while we have found available tiles. Oh, interesting. Because what I want is, I want to know that we've checked all the tiles, right? But I want to stop when we have hit the boundaries. So what we want to do is keep going in all the directions until we hit a boundary. Okay, so let's go like this. Let's go left. Go left, right. Because everything, like if we just did within, we have the player, right? And there are no tiles within one. Ooh, oh, close. So we do this in initial one. There's nothing. Then we have to keep going out. Initially, what I was going to say is that if we didn't find any available tiles, then stop. But that's not true, because if we go out by 1, we might not find any open tiles. But if we go out by 2, we'll find open tiles. So we just want to keep going out in all directions until we have hit an edge, and then when we hit an edge, we don't bother going out further, and in that case, we'll do something to indicate that we have exceeded the distance. So this means that we've gone out, and we'll figure this out in just a second. I don't know what this loop thing is going to be, but what we're going to do, just to make sure, is put this so that our app doesn't crash. This will keep us from having a bunch of headaches, but at least it'll let us know that something happened. Okay, so we're gonna go self, came from, we need to check all the tiles around the player. Technically, we want to check horizontal tiles before the angle tiles. So let's see, if we have 1, we want to go -1, +1, blah, blah, blah. When we go up to 2, I want to try the angles. I think we might just do this much simpler and just start here and actually do a grid. So technically, you might not get the absolute closest place, but you'll get a very close place. Okay, so so the locations that we're going to try are okay, so they're going to be from our goal minus left distance, and we're going to go from minus left distance to, this is not code, I'm just writing this so I can have it clear in my mind. Ooh, this is kind of a bigger algorithm, and I don't know that I'm going to be able to do this in like 40 minutes, which is the max that I want to spend on this. So for right now, we're not going to do this just yet. I'm going to try to figure this out next time, maybe. This will be a project for a future project. We're going to just put a note here. Because what I want to do is actually take an AI. Let's get a new strategy. What my thought process was that I want AI that follows the player. Great. Well, the AI is not going to be able to go to the player's tile. They're going to have to go to a tile next to the player. So how do I figure out which tile that is? Well, if I'm already doing that, I might as well write the code to make it go to the closest tile it can find near the player. But that is not necessarily good either. So let's just have it try to path to the player, and we'll just have it go to one of the sides. So that's going to be fairly simple. So what we do is, okay, get next location. Ooh. Okay, this one's pretty simple. So, okay, yeah. So what we want is we're going to do the same thing player does with its pathing. Where is its pathing? Okay. So let's take this. Paste that there for now. Okay, so remember we called it reverse path to remind ourselves that the path is actually going in reverse. So we're going to remove the end of the path, and we are going to use that as its new location, right? And let me just make sure that that's correct. Did we do map open to player? Yeah, return new location. And if not, then we swap going up and self.enemy location. What is self.? Oh yeah, that just means don't move anywhere. Self.enemy location. Okay. Okay, so we have our reverse path. We're going to get a new location. If it's open to the player, then we're going to go there, which means we're going to return new location. Else, we're going to return... I've already forgotten. Always keep around your old code because it makes it way easier. Okay, so yeah. If it's open, we're going to go to the new location. If it's not, we're going to go to enemy.location, which is its old location. Great. Okay, now we don't need this because we get our new location by pulling it from the path. Now, if it doesn't have reverse path, we need to get it a path. Let's do path to player. This is going to be our cool new function. We're getting a path to the player. Also, just want to check something real quick. Set target location. Yeah, here we're going to take this. This is the basis for our strategy. And let's add reverse path. That's great. Make sure. Okay, so what we want is get next location, get path to player. Great. Now what we did before is we just took the enemy location I and J, great, and moved off of that. What we actually want, for this strategy, we actually need to know where the player is. Okay, so let's go look at the enemy. Update target location, gets its next location from. Well, that's interesting. I don't know why we're passing self. We don't need to. Yeah, let's get rid of that. And then let's do player. And I don't think we need to keep track of it. We can actually just go to the forest map. Oh wait, do we do it? Yeah, get enemies. Let's see if we... Oh, we don't do it through here. Okay. So let's go look at our... what do we call it? Forest. We just need to look for the enemy updates. Okay, here we go. Self enemies updates. Okay, so we're gonna pass them the player. So now the enemies have access to the player. Cool. So what we're gonna do is this. Interesting. Oh yeah, the enemy. There we go. So enemy gets player, right? And now we've altered this so that get next location also gets the player. Great. And now that we have player, we're gonna do path to player. Path to player. Pass it along. Okay, now, and this, the reason I'm passing this along instead of like doing it when we create it and just always having a reference, so you know maybe we want to change players. Like if we have a multiplayer game, we can change which player. But in the future, I might put this in the creation and not pass it along every time. Like in the event that we don't have multiple players. Okay, so what we want to do is here, get path. So we want to start with our own location. That should be fine. That's, well, our target location is, I believe, player location. Our own location is self.enemy.location. And then the map. Yes, and we have access to the map. If the path exists, then let's go reverse path. Target location equals target location. Oh, do we need? I don't think we need to keep track of the target location in our case, because we're not. Yeah, let's try not keeping track of that. That's fine. Now this is almost there. Let's say enemy cannot pass the location. But remember, we can't go to the player location because we don't want the enemy to stand on the player. So what we're going to do is we're going to make a simple function. This is the one that we will eventually change if we have a better way. But we will, for now, we're just going to make this pretty simple. What I'm thinking about is that, let's say one of the tiles around the player has to be open. So what we're going to do is we're going to go player.player location. I want to verify that is correct real quick. Player location equals a new location. Yeah, good. One of our regular locations. Okay, if player location, let's see. That's interesting. I don't know why I'm checking. Oh yeah, I am checking if these are open to the player when it's pathing, because let's say that we have a door that then gets closed. So initially it's open and we have a path, but then it gets closed and it hits a wall. We want it to stop, get angry, or whatever. Okay, so if open to player, and okay, new location is going to be player dot player location dot I player dot player location dot J. Okay, that's exactly where the player is. Just trying to make the basis of this here. Okay. Now what we want to do, so first we're going to try -1. Oh, you know what? We want to try this in the order of which one is the closest. You know what? We're just going to do it this way for right now. It might mean that what this will mean is that if the left side of the player is open, the enemy will always go to the left side of the player. And then it'll check the right side, and then the top, and then the bottom. What would be better is if we actually did whichever one of these is, right, dependent on where the enemy is in relation to the player. So if the enemy is to the left of the player, we try left side of the player before we try right side of the player. But that seems like a lot more than we actually care about right now. Let's just get the enemy to the player. I think that will be enough for today. So, okay, so one of these needs to be open. So let's do else. That means that none of the tiles around the player are open, and that means the player is surrounded. That doesn't make a whole lot of sense, but who knows? That could be the case if we make a weird map where the player is locked in. Get closest location to player. Oh yeah, so we just need to return this. Okay. And these need to match, so this should be +1 here. It should be -1 here, and this one should be +1 here. There we go. Okay, cool. Now we've gotten the enemy to the character. Just looking through it to make sure nothing is weird. Okay, yeah. So that gets us as closest path to the player, or a closest location. Closest location to player, get the player, great. Now, so our target is not the player's location. Our target is the closest location. And I can't type. Okay, so that's our AI strategy 3. So let's make a new enemy that utilizes AI strategy 3. And let's give it another color. Let's give it like a dark green. Now let's do red. And that's actually blue anyway, but whatever. Let's make it red so that we can actually see it. Save that guy. Okay, so now we have an enemy 3. Oh yes, how do we indicate the AI strategy for enemies? Where did we do that? Oh, I know fast way to find out. Oh, so it's in here. So we are doing it somewhere here. Oop. Oh, here we go. Yeah, there's probably a nicer way to do this, but I'm not going to worry about it for right now. This is good enough. I mean, because we're actually building these, we're not saving these tiles, it's not a big deal. So we're not going to be saving this, so we can actually put this in here as like its AI strategy, which we may want to do later, but I'm not going to worry about that just yet. Okay, so let's drop in 3, and then let's see it blow up. Okay. AI strategy 3, line 48. Let's go find out what the deal is. Local path, self, A star. Okay, yes, we need a copy of A star. You know what? I think I'm just gonna do this. We're gonna make a global A star. So let's go to the main. And let's open the player. Let's copy this stuff over. So we're gonna get A star at the top level. There it is. This is now going to be our global A star. Great. Now we can just use it everywhere. Don't have to keep a reference to it around. Okay. Oh, whoops. You know, so let's add our enemy back. Now let's save this so that we always have that enemy. Okay, now let's play. And it's broken. 30-second target location. How do we have target location? What? Oh, I'm probably looking at the wrong file. Gotta scroll to the bottom. Okay. Enemy 37. Target location nil value. Okay. How do we get target location? Oh, you know what? That might be because I didn't set its target location. Where does it use target location? Its new location is less than target location. Oh, interesting. This gets the next location. If it's... Oh, it tells it... Oh, that's weird. Because in our new one, you just go to the new location. Like, the target location is the new location. This checks to see if it's open. Wait, I don't even know why we're doing this. If my new location is less than my target location. Oh, because this assumes that your target location is not the actual next place you're going to move to. It thinks your location, your target location is where you eventually want to go. It's not where you're currently going. It's not like a step in the path. So we actually need enemy to be slightly different in order to accommodate this. Okay. So what enemy needs to do in order to use this is it just needs to, on update, it just needs to get next location. And this next location is either going to give you the new location that's from our reverse path, or it's going to get a path to the player me just, I think this is the problem. So we're not returning anything in this scenario. So like when we go and we get the path to the player, let's just wait for a second. It doesn't have to go immediately running after the player. Hey, look, there it goes. So now if I go here, look, I got my little shadow, but remember he always stays to my left side. Isn't that cool? So now we have an enemy that follows the player wherever the player may go. It's like one step behind. Because it's got to figure out what it's doing before it decides to attack. So that gets us the basis of this. Now what we're going to do is we are going to... I wonder if there's like an even easier way. I just realized to like get the enemy to whatever side. If he's coming up, and let's see, steps to any side, like this one, and it's already next to the player, like you could just say, stop there. I wonder if that would be sufficient enough. I mean, with obstacles and stuff, it will end up walking around, but that's probably actually good enough. So let's go take a look at that. That's probably... So get next location. Huh. Okay. If... What I hate is like we just want to know if it's one of the ones around the player, like if it's already next to the player. Oh, if it's already next to the player, and that means the I or the J equals interesting. Okay, let's try this. Okay, so if a new location I equals player.playerLocation.I or new location.j equals player.playerLocation.j, then if new location.I equals player dot. Okay, so what I'm doing here is I'm saying like if it's I or it's J is in line with the player. So it's directly to the left or directly above, or it's in this line, this vertical line above the player, or it's horizontal line, right? If it's that, then check if one of its locations is right next to the player. And what that'll do is it's like a quick way to say like, hey, I'm right next to the player. This could be a nice fancy way to do it. Another way would be to get its absolute value distance from the player. Oh, that's what we could do, is absolute value distance of the player. Interesting. Sorry, I'm just thinking about how we might want to do that other AI that we talked about. This needs to be I. This needs to be I. This needs to be J. J. Okay, so let's see. If its I is in line with the player location's I, so it's in a horizontal line with the player, let's say. Well, its I location is not going to be player's I plus 1 or minus 1 because we've already established it's equal. But if its J is plus 1 or its J is minus 1, that means it's right next to the player. Likewise, if its new location J is equal to the player's J, that means it's in a vertical line with it, then if it's I is +1 or it's I is -1, that means that it's right next to it. Perfect. So that means that we're right next to the player. So we're gonna cut this. So we're gonna say, hey, I'm in a place that's open, an open location, just to make sure we're in an open location. Then this means we're already right next to the player. In that case, we want to do whatever is, so what we want to do is take self.reversePath and make it null, or make it empty. Return it to an empty path. Actually, we can just make it nil. And then what we're going to find is that self-reverse-path doesn't exist. So we're going to get a path to the player. Get path to player. It's going to set self-reverse-path. Okay, so what do we rake? Line 26. Okay, that's fine. I messed up some parentheses here. Oh, are you not able to continue onto another line? Ooh, that would be really dumb. Maybe I can do the or here. Well, let me do that, maybe. Parenthesis expected near equals. Let's see if we can do. If it's not considered completely double command, I don't like that. That's not what we're talking about. Want to know what happened? Ooh, some Lua tricks you may not have known. And it's dead. Great. Multi-line prints, that's great. We don't care about that. What I want is a multi-line if statement, because it looks terrible if you have 1,000 lines. Blah blah blah. Numbers, booleans, metatables. All right. Well, I might read this later because it looks like it could be a fascinating read. But for now, we don't care. We're just gonna try to finish this. So let's just put it on one really big line because Lua is making us. What? Oh, maybe it's just that I missed something somewhere else. Blah blah blah, or blah blah blah, or blah blah blah. Oh, that's what it is. Okay. Should just be these equal signs. There we go. Okay. Ah, here we go. See, now the enemy goes to whatever side is nearest, and it doesn't look so crazy. It still could probably be better, but hey, this is good enough for right now. Enemy could not path. Why are we getting so many could not path to location? I don't know why. Anywhere that the player is going. Oh, now it's just could not path, could not path, could not path. Okay. Yeah, well, we'll use this for right now. We're gonna make this better later. to make it so that it doesn't keep trying to find a path when the player is right next to it. Oh, that's interesting. Well, it should be a problem here. Because it should just be trying to find. Let's see what happens real quick. I mean, could not find path to location. Oh yeah, so that's what I want to see. Let's print what. Just try to find out where it's trying to path to that it can't path to when it's standing right next to the player. Okay, so let's play. Let's see what happens. Could not path to location. Oh, is there somewhere else that it says could not path to? Oh, is that maybe the player not being able to path to location? Oh, wait. What did I just do? Oh, closest location. Separate check. Closest location is 13.4. And it could not path to location. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 1, 2, 3, 4. So it's at its own location. It's already there. It could not path to locations. Let's take a look. A star. Wait, which one are we using? We are using just regular A star, I believe. Yeah, we're just using global A star. Get path. Okay, so let's go look at our A star. What I want to do is start going. Oh yeah, because it's gonna go through the neighbors and blah 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 blah. What I want to do. What if get actual path came from. What I want to do is say like if start equal start dot I equals goal dot I and start dot J equals goal dot J. Already there. Let's see. Nope. Still could not go to location. Why? 13.9. Okay. Closest location. Oh. Location right next to it. I'm just gonna do this. We're gonna see real quick what's going on. Okay, what happened here? Let's get to the bottom of this. Okay. Okay. Could not path to location. Look at that. They're the same. I thought I just changed our AI strategy. Oh, did I not save this? No, I did save this. Oh, it's nil. Yeah, enemy could not path to location. That's... Oh, yeah, so that's why it's spamming could not let path to location, because, hey, it can't path to location. It's already there. But what if instead, in that case, we just said, like, hey... Ooh, I'm a little worried about this. Let's... see if there's a nicer way to create an array. Oh, okay, yeah, we can just do that. So it should just be this. I think what's going to happen now is it's just going to hide it. Yeah, closest location. So it's still running this and getting closest location. But like it's not saying this because it's actually trying to send it to the player to that location. It's just continually sending the player to the location they're already at. That could be fine for now. Yeah, let's just leave it. Cool. I think that's it. I think that's good. We finally got our A-star strategy going, and now we have applied it to an enemy. So that's pretty cool. Now we can actually run it and see an enemy chase down the player, in addition to our dumb enemies that just run back and forth. This is also going to allow us to make more interesting pseudo AI where like somewhere between these two, where an enemy will pick a location that it thinks is nearer to the player, but not necessarily directly on the player. Cool. So there we go. There you have it. I hope that is helpful. Again, I'm about to go add all this code to the GitHub /github.com/TylerMakes. Bulbasaur is the application. Just to make sure that is very visible on the screen, I can put it like here and do this. Hopefully you can read that. If you couldn't read anything before, that would be really sad. If I was doing this whole stream at a level that was too small for people to read. I think that's good. Now I just should have counted so that I know what size I like. Anyway, there you go. Go check it out, get the code, enjoy it. Let me know if there's anything that you do with it, and if there's anything you'd like to do, like if you'd like me to get into some particular part of programming this game sooner rather than later, let me know, because you can affect the outcome of this game by just telling me what is most important to you and would be helpful to you. So anyway, like, subscribe, do all the social stuff, share it, get it out there. And yeah, happy programming. See you later.